Good day, class. For our first lecture to AMT 225, Aircraft Communication and Navigation System. Based on our handout 1, early aviators began the challenge of increasing operational safety and functionality of flight after securing the mechanics of flight. They have mostly developed thanks to the usage of dependable communication and navigation technologies. With thousands of planes in the air at any given moment, communication and navigation systems are critical to ensuring safe and successful flying. The process of development is ongoing. On the flight deck, smaller, lighter, and more powerful communication and navigation system improve situational awareness. The progress of aviation electronics, when combined with enhanced display and management control system, is expected to improve aircraft safety. One of the first advancements in the use of electronics in aviation was clear radio voice communication. Soon after, navigational radio appeared. There are plethora of electronic navigation and landing aids available today, like weather, collision avoidance, automatic flight control, flight recording, flight management, public speaking, and entertainment system, all benefits from electronic gadget. Avionics is a word derived from the combination of aviation and electronics. It was first used in the USA in the early 1950s and has since gained wide-scale usage and acceptance. Although it must be said that it may still be necessary to explain what it means to the layperson or occasions. The term avionics system or avionics subsystem is used in the presentation or in this presentation to mean any system in the aircraft which is dependable on electronics for its operation, although the system may contain electromechanical element like the example of the fly-by-wire on the next slide. For example, a fly-by-wire or FBW flight control system depends on electronic digital computers for its effective operation. But there are also other equally essential elements in the system. This includes solid-state rate gyroscope and accelerometer to measure the angular and linear motion of the aircraft, and air data sensor to measure the height, airspeed, and incidence. There are also the pilot's control. These are the stick and rudder sensor assembly and electro-hydraulic servo actuator to control the angular position of the control surface. The avionics industry is a major multi-billion dollar industry worldwide, and the avionics equipment on a modern military or civil aircraft can occur for around 30% of the total cost of the aircraft. This figure for the avionics content is more than 40% in the case of a maritime patrol or anti-submarine aircraft or a helicopter, okay, and can be over 75% of the total cost in the case of an airborne early warning aircraft or AWACS. The avionics system are essential to enable the flight crew to carry out the aircraft mission safely and efficiently. Whether the mission is carrying passenger to their destination, in the case of civil airliner, or in the military case, intercepting a hostile aircraft, attacking a ground target, reconnaissance, or maritime patrol. A major driver in the development and introduction of avionics system has been the need to meet the mission requirements with a minimum flight crew. In the case of the modern civil airliner, this means a crew of two only, namely the first pilot or the captain and the second pilot. This is only made possible by reducing the crew workload by automating the tasks, which used to be carried out by the navigator and flight engineer. The achievement of safe two-crew operation has very considerable economic benefits for the airline in a highly competitive market, with the consequent saving of crew salaries, expenses, and training costs. The reduction in weight is also significant. It can be translated into more passengers or longer range on less fuel. This is because unnecessary weight is geared up to 10 or 1 to 10, as we'll explain later. Uh, in the military case, a single seat fighter or strike or attack aircraft is lighter and costs less than an equivalent of two-seat version. The elimination of the second crew member, which sometimes this is the navigator, observer, or radar operator, has longer significant economic benefit in terms of reduction in training costs. So this cost of training and selection of aircrew for the fast jet operation is very high. So other very important drivers for avionics system are increased safety, air traffic control requirements, all-weather operation, reduction in fuel consumption, improved aircraft performance and control and handling, and reduction in maintenance costs. Military avionics systems are also being driven by a continuing increase in the threats posed by the defensive and offensive capabilities of potential aggressor. The role played by the avionics system in modern aircraft in enabling the crew to carry out the aircraft mission can be explained in terms of a hierarchical structure comprising layers of specific tasks and avionics system functions. As shown in the figure, this shows the prime or core function, which are mainly common to both military and civil aircraft. It must be pointed out, however, that some avionics systems have been left off this diagram for clarity. For example, air traffic control or ATC transponder system, the ground proximity warning system or GPWS, and the threat alert or collision avoidance system or TCAS are mandatory equipment for civil airliners. GPWS provide a warning by means of visual display and audio signal that the aircraft is on a flight path that will result in flying into the terrain, and that action must be taken to change the flight path. TCAS provide an alerting and warning display of other aircraft in the vicinity in terms of their range, course, and altitude together with the advisory collision avoidance command. It can be seen that the main avionics subsystem have been grouped into five layers according to their role and function. These are the man-machine interface, aircraft state sensors, navigation, external world sensor, and task automation. The system interface directly with the pilot. This compromise display, communication, data entry and control, and flight control. The display system provides the visual interface between the pilot and the aircraft system and compromise head-up display or HUD, helmet-mounted displays or HMD, and head-down display. or HDD. Most combat aircraft are now equipped with HUD. So, a small but growing number of civil aircraft have HUD installed. The HMD is also an essential system in modern combat aircraft and helicopter. The prime advantage of the HUD and HMD are that they project the display information into the pilot's field of view so that the pilot can be head up and can concentrate on the outside world. The HUD now provide the primary display for presenting the essential flight information to the pilot. And in military, aircraft has transformed weapon aiming accuracy. The HUD can also display a forward-looking infrared or FLIR video picture one-to-one with the outside world from a fixed FLIR imaging sensor installed in the aircraft. The infrared picture merged naturally with the visual scene, enabling operations to be carried out at night or in condition of poor visibility due to the haze or clouds. The HMD enables the pilot to be presented with information while looking in any direction as opposed to the limit or to the limited forward field of view of the HUD. An essential element in the overall HMD system is the helmet tracker system to derive the direction of the pilot's sight or line of sight relative to the aircraft axis. This enables the pilot to designate a target for the aircraft missiles. It also enables the pilot to be cued to look in the direction of a threat or detected by the aircraft defensive aid system. The HMD can also form of an indirect viewing system by driving a gimbal infrared image sensor to follow the pilot's line of sight. Image intensification devices can also be integrated into the HMD. This provides a complementary night vision capability enabling the aircraft or mostly helicopter to operate at night or in a poor visibility. Next, the multifunction color display provide the primary flight display or the PFD. It has the information of the height, airspeed, Mach number, vertical speed, artificial horizon, pitch angle, back angle or bank angle, and heading, and the velocity vector. So they provide the navigation display or horizontal situation indicator, which show the aircraft position and track relative to the destination or waypoints, together with the navigational information and distance and time to go. The weather radar display can also be superimposed on the HSI display. Engine data are presented on multifunctional color display so that the health of the engines can easily be monitored and divergence from the norm highlighted. The aircraft system, for example, electrical power system, hydraulic power system, cabin pressurization system, and fuel management system can be shown in easy to understand line diagram format on the multifunction display. The multifunction displays can also be reconfigured in the event of a failure in a particular display. Color head-down display have revolutionized the civil flight deck with multifunctional display, eliminating the inflexible and cluttered characteristics of 1970s generation flight decks. which there are numerous dial type instruments display dedicated to displaying one specific quantity only. The communication system play a vital role. The need for reliable two-way communication between the ground bases and the aircraft or between the aircraft is self-evident and is essential for air traffic control. A radio transmitter and receiver equipment was in fact the first avionics system to be installed in an aircraft and goes back as far as 1909 by the Marconi Company. So the communication radio suite on modern aircraft is a very comprehensive one and covers several operating frequency bands. Long-range communication is provided by high frequency or HF radio operating in a band from 2 to 30 megahertz. Near to medium range communication is provided in civil aircraft by very high frequency or VHF radios operating in a band of 30 to 100 megahertz. And in a military aircraft by ultra high frequency or UHF radio operating in the band of 250 to 400 megahertz. So VHF and UHF are line of sight propagation system. Equipment is usually at the duplex level of redundancy. The VHF radios are generally at a triplex level on a modern airliner. Satellite communication or SATCOM system are also installed in many modern aircraft, and these are able to provide a very reliable worldwide communication. Okay, remember satellite communication or SATCOM. The aircraft state sensor system, this compromise the air data system and the inertial sensor system. The air data system, as shown on the slide, provide accurate information on the air data quantities, that is the altitude calibrated airspeed, vertical speed, true speed, Mach number, and airstream incidence angle. This information is essential for the control and navigation of the aircraft. The air data computing system computes these quantities from the outputs of very accurate sensor, which means the statistic or static pressure, total pressure, and the outside air temperature. The airstream incidence angle is derived from airstream incidence sensor, while the inertial sensor system provide information on aircraft attitude and the direction in which it is heading, which is essential information for the pilot in executing a maneuvering or maneuver or flying in a condition of poor visibility, flying in clouds or at night. Accurate attitude and heading information are also required by a number of avionics subsystems, which are essential for the aircraft mission. For example, the autopilot and the navigation system and weapon aiming in the case of military. The attitude and heading information are provided by the inertial sensor system or systems. This comprise a set of gyros and accelerometers which measure the aircraft's angular and linear motion about the aircraft axis, together with a computing system that derives the aircraft's attitude and heading from the gyro and accelerometer outputs. Modern attitude and heading refers system or AHRS use a strap down or body mounted configuration of gyros and accelerometer as opposed to the earlier gimbaled system. So the use of very high accuracy gyros and accelerometer to measure the aircraft motion enable an inertial navigation system, or what we call INS, to be mechanized, which provide very accurate attitude and heading information. Together with the aircraft velocity and position data, when we say position data, this is the ground speed, track angle, and latitude, longitude coordinates. The INS is in conjunction with the air data system, also provide the aircraft velocity vector information. The INS is thus a very important aircraft state sensor system. Remember, it is also completely self-contained and does not require any access to the outside world. Next, navigation system. The navigation system is accurate navigation information. That is the aircraft position, ground speed, and track angle, or the direction of motion of the aircraft relative to the true north, is clearly essential for the aircraft missions. Whether civil or military, navigation system can be divided into dead reckoning system and position fixing system. So both types are required in the aircraft. So for the dead reckoning navigation or dead reckoning navigation system, derive the vehicle presence position by estimating the distance traveled from a known position from a knowledge of speed and direction of motion of the vehicle. They have the major advantage of being completely self-contained and independent of external system. The main types of dead reckoning navigation system used in aircraft are inertial navigation system. So the most accurate and widely used system are Doppler or heading reference system. These are widely used in helicopters. Air data heading reference system. These are the system which are mainly used revisionary navigation system, being of a lower accuracy than inertial navigation system or Doppler or heading reference system. The position fixing system used are now mainly radio navigation system based on satellite or ground-based transmitter. A suitable receiver in the aircraft with a supporting computer is then used to derive the aircraft position from the signal received from the transmitter. The prime position fixing system is without a doubt. This is the GPS or Global Positioning System. So this is a satellite navigation system of outstanding accuracy, which has provided a revolutionary advance in navigation capability since the system started to come into full operation during or in 1989. Approach guidance to the airfield airport in condition of poor visibility is provided by the ILS or Instrument Landing System or by the latter MLS or the Microwave Landing System. So a full navigation suite on an aircraft is hence a very comprehensive one and can be include INS, GPS, VOR, DME, ILS, and MLS. Many of these systems are at duplex level and some may be at triplex level. Although this will be discussed as our lessons goes by. Next, the task automation system. So this compromise the system which reduce the crew workload and enable minimum crew operational by automating and managing as many tasks as appropriate so that the crew role is a supervisory management one. Navigation management compromise the operation of all the radio navigation aid system and the combination of the data from all the navigation sources to provide the best possible estimate of the aircraft position, ground speed, and track. The system then derived the steering commands for the autopilot so that the aircraft automatically follow the plan or the navigational route, including any changes in heading as particular waypoints are reached along the route to the destination. It should be noted that this function is carried out by the flight management system or FMS if it is installed to the aircraft. Then the autopilot and flight management system have been grouped together because of the very close degree of integration between this system on a modern civil aircraft. It should be noted, however, that the pilot or that the autopilot is a standalone system and not all aircraft are equipped with an FMS or flight management system. So basically, for the autopilot relies the pilot or of the need to fly the aircraft continually with the consequent tedium and fatigue, and so enable the pilot to concentrate on the other tasks associated with the mission. Apart from basic modes such as height, hold, and heading hold, a suitably designed height integrity autopilot system can also provide very precise control of the aircraft flight path for such application as automatic landing in poor or even zero visibility condition. In military, applications and autopilot system in conjunction with a suitable guidance system can provide automatic terrain following or terrain avoidance. This enables the aircraft to fly automatically at high speed at very low altitude or at about 100 to 200 feet so that the aircraft can take advantage of the terrain screening and stay below the radar horizon of enemy radars. On flight management system, okay, to expound our lesson, sophisticated FMS have come into wide-scale use on civil aircraft since the early 1980s and have enabled to crew operation of the largest long-range civil jet airliner. The tasks carried out by the FMS include the following: flight planning, navigation management, engine control to maintain the planned speed or Mach number, control of aircraft flight path to follow the optimized plan route, control of the vertical flight profile, ensuring the aircraft is at the planned 3D position at the planned time slot, often referred to as the 4D navigation. This is very important for air traffic control. The flight envelope monitoring and minimizing fuel consumption. Engine control and management system. So the engine control and management system carry out the task of control and the efficient management and monitoring of the engine. The electronic equipment involved in modern jet engine is very considerable. It forms an integral part of the engine and is essential for its operation. In many cases, some of the engine control electronics are physically mounted on the engine. Many modern jet engines have a full authority digital engine control system or PADEC. Okay, so this automatically control the flow of the fuel to the engine combustion chamber by the fuel control unit so as to provide closed loop control of the engine thrust in response to the throttle command. So the control system ensure that the engine limit in terms of temperature, engine speed, and accelerations are not exceeded, and the engine responds in an optimum manner to the throttle command. So that the system has what is known as the full authority in terms of the control it can exercise on the engine and a high integrity failure survival control system is essential. Otherwise, a failure in the system could seriously damage the engine and hazard the safety of the aircraft. A FADEC engine's control system is that or thus similar in many ways to the FDW flight control system. So before I proceed with the housekeeping management, other very important engine avionics system include engine health monitoring system, which measure the process and record a very wide range of parameter associated with the performance and health of the engine. So this give early warning of engine performance deterioration, excessive wear, fatigue damage, high vibration level, excessive temperature level, and etc. Okay. So next for our housekeeping management system. So basically housekeeping management is the term used to cover the automation of the background tasks which are essential for the aircraft safe and efficient operation. Such tasks include fuel management, electric power supply system management, hydraulic power supply system management, cabin or cockpit pressurization system, environmental control system, warning system, maintenance and monitoring system. On the next slide, so for the avionics system requirements, basically class the key to an avionics system or subsystem design which provide dependable service at low cost of ownership is the requirements definition. No? But requirements engineering is now a recognized field considered by a major professional societies such as the IEEE as one of the initial step in system engineering as well as subsequent step in the development process illustrated in the slide. This figure presents a key process that result in a reliable and affordable avionics system. These process are setting requirements, reliability allocation, design analysis using simulation and modeling, validation of the design using formal methods, and process for certification. The important issue of electronic magnetic effect on the design and operation of avionics is also addresses. Aircraft functional requirements are at the top of the requirements hierarchy. The aircraft mission is broken into phases, including pre-flight checkout, taxi out, taxi off, or take off, cruise, descent, landing, roll out, taxi in, and post-flight and so forth. Additional specialized mission phase such as weather diversion, cargo drop, electronic warfare, etc. also drive the aircraft performance requirements. Typical aircraft functional requirements include ground steering and braking, passenger comfort, navigation, communication, and environmental conditioning. The figure on the slide shows the breakdown of functional decomposition of requirements from the aircraft level to the avionics function level. Requirements must be traceable and justified. In some cases, every shell is numbered and then accounted for in test plans to demonstrate that it has been met. Okay? For the mission segment, segment requirements, and so forth. One of the avionics system requirements are the preliminary design requirements. What should be the size, the weight, the purpose, the accuracy of the avionics system? How many number of systems? Electrical power specification and environmental specification. While after looking or studying the preliminary design, we will now move to the detailed design for the body. Okay? Under detailed design, these are the selection of the components or material, what software or hardware to be used to develop this system. Development of algorithms, simulation, and coding. So software based. PCB design and fabrication of the hardware, and mechanical design and chassis. Lastly is the testing of the reliability check and acceptance. Major entities of avionics system are capability, reliability, maintainability, availability, certificability, survivability for the military, susceptibility, and vulnerability. So let's look each entities of the avionics system. For the capability, the question is how capable is the avionics system? Can they do the job and even more? Designer to maximize the capability of the system within a constraint that are imposed. Then for the reliability, the designers strive to make the system as reliable as possible. Okay? High reliability equals less maintenance costs. If less reliable customer will not buy it, and in terms of civil airliners, the certificating agency will not certify it. Third, maintainability are closely related to reliability. System must need preventive or corrective maintenance. System can be maintained through built-in testing, automated troubleshooting, and easy access to hardware. Fourth is the availability, a combination of reliability and maintainability. Test runs and for sorties. This is for military aircraft use. Fifth is the certificatability or certificability. Major area of concern for avionics in civil airline. Certification conducted by the regulatory agencies based on detailed, expert examination of all aspects of aircraft design and operation. The avionics architecture should be straightforward and easily understandable. Survivability. It is a function of susceptibility and vulnerability. Susceptibility measure the probability that an aircraft will be hit by a given threat, while the vulnerability it measure the probability that damage will occur if there is a hit by the threat. Weight and power. So minimizing the weight and power requirements are two fundamental concepts of avionic design. So the design must be lightweight and power consuming, which is possible through the data bus and latest advancement of electronic devices. And lastly, the integrated of avionics. So why we need to integrate avionics in the aircraft? So there is a need for a system integration, combination of subsystem, weapon system concept in the mid 1950s or during the World War, naval strike aircraft system, avionics architecture. So until today, we integrate avionics to all aircraft and point-to-point wiring. Lastly, the multiplexing or the TDM and data buses. So that will be all for our first lesson on introduction to avionics or communication and navigation system. Thank you.